Okay. Now we're going to do a problem on specific heat capacity. This is really a problem for states of matter, the chapter on states of matter, okay, where this is what I want to do. I want to determine the amount of energy it takes to change ice at negative 20 degrees Celsius. What is the phase of water at negative 20 degrees Celsius? Is it liquid, solid, or gas?
Solid.
It's a solid, right. And how many degrees does it take to melt? How many degrees to get it to 0 degrees? 20, right? Good, excellent. All right, good. So let's do this problem, okay? I want to take, shall we keep it simple? We're going to do 1 kilogram of ice. Yes, is that all right? So 1 kilogram of ice at negative 20 degrees Celsius. This is degrees Celsius. So we're going to start there, and we're going to heat it up until it's 0 degrees. And what's going to happen at 0 degrees? What's going to happen? Is it going to go to 1 degree or 2 degrees? What's going to happen when it gets to 0 degrees? And you keep adding heat. Yes? It's going to plateau there. And what does that plateau mean, Jen? That's right, that's a plateau. Does anybody know what that plateau means? Well, I'm going to tell you what it means. That means that it's still absorbing energy, isn't it? Is it still absorbing energy? But is it kinetic energy? It's weird because it should be kinetic energy, right? But it's not kinetic energy, is it? What is it?
Potential.
Who said that? 2 points for the Danish team. Excellent. We're going to get a gold today. Yeah, it's potential energy. So the potential energy is increasing. So it's plus a change in potential energy. And what is that change in potential energy called at 0 degrees Celsius? What is it called? I'll give you the abbreviation and then you see if you can name it. Anybody? Sounds very nuclear. What does F mean? And when you see the word F and you're doing nuclear stuff, what do you think of?
Fusion.
You think of what?
Fusion.
Yeah, fusion, the heat of fusion. That's right. And the heat of fusion of water is 80 kilojoules per kilogram. Okay? Has anybody come up with the specific heat of ice in calories or kilocalories?
Yes.
What do you got?
2.10 kilojoules.
No, I don't want kilojoules. I want calories. We can convert that maybe, but let's do calories. So I'll continue with mapping out the problem because we may not get time to finish it today. So this will be part 1, specific heat capacity, okay? All right, so now it's all melted and it's going to raise the temperature. And to what temperature is it going to go? Is it going to go to 1,000 degrees or 1,000,000 degrees? As you add heat, it's going to increase temperature, true or false?
True.
It's going to increase its kinetic energy, true or false?
True.
Excellent. And what is it?
So the boiling point.
To the boiling point, it'll stop and then do what?
The potential energy will increase.
And then very good. God, I love it. Yeah, the temperature will stop rising and the potential energy will increase. Could somebody interpret that? It's very difficult understanding Danish. Were you speaking Danish or were you speaking English? Yeah, but we need an interpretation. We need a English interpretation spoken by a Dane. Danes are very brilliant. So what did he actually say? He said it's going to go up to 100 degrees and plateau. Didn't he say that? Yeah, exactly.
Not necessarily 100 degrees.
Exactly. It depends on the what?
Outside pressure.
Excellent. Yeah, it depends on the outside pressure, the external pressure. Excellent. We're going to assume that the pressure is specifically and absolutely sea level, and it's 1 atmosphere. Okay? So it's going to boil. We're going to say it's going to boil at 100 degrees. And then it's going to rise again, and we're going to say that it's going to go to 120. Okay? Yes? We know the specific heat capacity of water is 1 kilocalorie per kilogram degree Celsius, or calorie per gram degree Celsius, or kilocalorie per kilogram Kelvin degree, right, Kelvin, because the size of the Kelvin, the size of the Celsius is the same, okay? The heat of, what's the heat that goes in to increase the plus potential energy? You're going this way. What are you doing when you go this way? You're going to lose, right? Right?
Yes.
Shall we get rid of this here and put this? Right? Yes? What's the heat of vaporization for water? Anybody know? It's going to be 540 kilocalories per kilogram. Did I put kilojoules? Sorry. Kilocalories, my apologies. Is that what you kind of like were neat? Did you see that? I made that mistake? Okay. So what is the specific heat capacity of ice? Did we find that? You didn't find it? What is it in joules? Anybody? What is it in joules? And I need the specific heat capacity for gas, water in the gaseous phase. Okay, while they are looking for that, I will continue. Okay? So there's going to be 5 heats. Do you see 5 separate heats? There's going to be a heat that's going to be right here. We're going to call that Q1. And that heat is going to heat it from negative 20 degrees Celsius to 0 degrees Celsius. Is that okay? There's going to be a second heat, Q2, that's going to add the potential energy to the ice to go from 0 degree solid to 0 degree liquid. And that heat is going to be called Q2. Correct? Now, it's 0 degree liquid, and you want to go to 100 degree liquid. We're going to call that Q3. Okay? Now, you want to go from 100 degree liquid to 100 degree gas. And we're going to call that Q4. Q4. Correct? That's going to be Q4. Now, we are at 100 degree gas and we want to go to 120 degree gas. We're going to call that Q5. Excellent. We're going to call that Q5. So this is Q1, Q2, Q3, Q4, Q5. This is time that the heat is being absorbed, okay? Now, right over here we'll write the different Qs, okay? So, Q1 is going to equal M delta T C. C is the specific heat capacity, and it's going to be for the solid, ice, correct? Q2 is going to be the mass times the heat of fusion. Is that easy? Yes? Q3 is going to be the mass times the change in temperature times the water, times the liquid water. Correct? Q4 is going to be the mass times heat of vaporization, and Q5 is going to be the mass times the change in temperature times C for the gas. Are we all right with that? Yes? Okay? All right. So, that's the end of part 1. Part 2, we'll start to fill in some numbers. Clear? Is that okay? And what I'll do is, when we come on screen the next time, I'll have all of the values here in red. Heat of vaporization, heat of fusion, specific heat capacity of ice, specific heat capacity of water, specific heat capacity of steam. Clear? We're off.